Well, just remember that trig form is going to be r times cosine of theta plus I times sine of theta. That means I need to get an r value, I need to get a theta value. R value is always the easiest because r is just going to equal the square root of either a squared plus b squared or the square root of x squared plus y squared. In this case, we have a and b. Doesn't matter what you call them. It's just your first number, second number. So we're going to have negative 3 squared plus 3 squared. And we can write bigger than that. So we're going to have r equals the square root of 9 plus 9, so square root of 18. 9 goes into 18, so I can rewrite 18 as 9 times 2. So I can rewrite this as 3 square root of 2. That is my r value. The next thing I need to get is that direction angle, or that theta. So no matter how I do that, I should always have a drawing. We don't always have to draw it this big, but I have the space, so I'm going to draw it that big. Okay, we are going to say that we're looking for the point negative 3, 3. So negative 3, 1, 2, 3, 3, 1, 2, 3. That point would be about there, so that is our negative 3, 3 on our complex plane. Now to get my direction angle, I can either, well, we always are going to draw a vector going to it. I can either drop this, and we have to remember that our angle is this one. So if I solve for this angle, I'd have to do 180 minus that angle. 180 minus this angle would get me this full thing. The other way I could draw it, and which way I'm going to finish it, is I could draw it this direction. Once again, this full thing is my theta. So I'm just going to call this little angle here alpha. So when I find alpha, I have to add 90 onto it, because 90 plus this little angle is going to give me my total arc. All right, this triangle is negative 3, 3, so that means it has negative 3 there, and I have a height of 3 there. Okay. So that means to get my alpha, I need to use tangent. So we're going to say alpha equals the tan inverse of TOA, which is opposite over adjacent, so negative 3 over 3. And that is going to equal 45 degrees. I think it actually comes out to negative 45, right? If you did it, it should come out to negative 45. But it doesn't matter whether it's negative or positive, we're always going to take the positive form. Because if I did 90 plus negative 45, I would come up with 45 degrees, which wouldn't make sense because this angle is bigger than 45 degrees. So we have to take the positive version no matter what. And so we're going to have 90 degrees plus 45 equals 135 degrees. So my theta equals 90 plus whatever that angle is. That means my value, or my trig function of this, is going to be the r, which is 3 square root of 2 times cosine of whatever my theta was. Now it's 135 degrees. Plus I times the sine of that theta, which is 135 degrees. We had a good question in the last class. They're like, how do you know to use tangent or when to use that cosine? Because even in the homework on the answer guide, some of them they did cosine, like they did that a equals r times cosine theta, plug stuff in. And my answer to that is it doesn't matter which one you use. Okay, in fact, I'm going to use the other method right now. So one method is to draw your triangle, solve your angle, and either add it to 90 or subtract it. The other method that you can use, rather than using tangent, is I can say that I know that a equals r times cosine of theta. That should be one of our equations that we have burned into our mind. Well, I know my a is negative 3. I know my r now is 3 square root of 2 cosine theta. We're pretending like we don't know theta. So I'm going to divide both sides by 3 square root of 2. I need to take cosine inverse. So this is going to be theta equals cosine inverse of negative 3 over 3 square root of 2, which is also going to equal 135 degrees. All right, so this method does not involve you drawing a triangle, but you should still plot your point. We should have everyone looking up here because this is 2 good methods. All right. I traditionally prefer this one because I don't have to draw a triangle and figure out which was my opposite. I can just plug this equation in. I can plot my point real quick to make sure 135 makes sense. Yep, 135 would make sense. So that would be my answer. So if you get this way down, it goes a little bit quicker. Not super quick. I mean, the other one you just have to draw a negative 3 and 3 and just figure out your tangent. But no matter which method you use, please do me the favor of drawing your angle to make sure it makes sense. Because sometimes this equation is going to find your reference angle. It's going to find this angle. So let's say this came out as 45 degrees. You would tell yourself, well, 45 degrees doesn't make sense. It's going to be 180 minus 45 to get me back up here, and it'd be 135. So the only way you're going to realize that is if you draw a picture to understand that your angle has to be bigger. Okay? Whatever method you choose, kind of choose now and just keep repeating it so you don't go back and forth and mess up on the test. Pick one and work with that method. Whatever one you've been doing better on, work with that method. All right, any questions about the 2 methods? I don't want to confuse anyone. If you draw the triangle, just stick to drawing the triangle. Okay, don't be like, oh, when do I use cosine? This is just a completely different method of doing it. All right, I'm going to go ahead and I'm going to get right into the lesson. If you have questions, please come see me or post my Edmodo. And the reason why I'm doing that is because most of those problems that we did yesterday are repeated problems just with different names attached to them. It's still basically just doing this. All right, so if you have questions, please come see me. Plus, we don't have time because we have shortened class periods. All right, today we're going to talk about plotting polar equations. Now, when we plot polar equations, it works just like rectangular. When we did a rectangular, we started out when we did rectangulars by just pointing plots and connecting lines, all right, to figure out shapes. And then we got more advanced where we started coming up with parent equations so we could draw a general shape of it and we get key points to know what it is. The same thing is going to work with polar equations. We're not going to spend enough time to really make super accurate drawings like we could with the rectangular because we have one day to do what we spent a whole section on in rectangular. So we're going to very briefly cover everything just so you can see it's basically the same. And we're going to learn how to use our calculator to do the heavy lifting for us. All right, so we're going to start off by doing the plotting points to figure out what something looks like in polar coordinates. So I made kind of a table to work us up to coming up with our ordered pair. I do want to write down that our ordered pair is always going to be our length r and theta. So instead of x and y, we have r and theta. Okay, so first thing we're going to do is we're going to take the cosine of 0 degrees. Well, cosine of 0 degrees is 1. And 5 times 1 is going to be 5. So that means our ordered pair is going to be length 5. And our degree was 0 degrees. Plotting this, our length is 5. So we go to our polar axis and we count out 5. 1, 2, 3, 4, 5. I have no degree, so I'm not shifting either up or down. So we're just going to put a point right there. 1, 2, 3, 4, 5. It's just like the point 5, 0. On our next one, we're not going to do square roots or anything. We're actually going to just put decimals down. And the cosine of 30 degrees is going to be 0.87. 5 times 0.87 is going to round to 4.4. And so our ordered pair is going to be 4.4 30 degrees. So plotting that, I would count out 1, 2, 3, 4.4, and I'm going to raise that up to, what did I say, 30 degrees, so the point's going to be about here on that 30 degrees. All right, I'm going to skip down to, do you see that 105? I don't want 105, I actually want that to be 120. And I'm going to help you fill out 120 real quick, because that has negatives in it. Well, the cosine of 120 degrees is negative 0.5. 5 times that is going to be negative 2.5. And so we're going to have negative 2.5, comma 120 degrees. Remember, when we plot negatives, when I plot negatives, I'm not going to go to 120 and go 2.5. All right, I'm not going to go to 120 and go 2.5. What we can do, though, we have kind of two methods to plot these, okay? We can go to 2.5 and then go around 120 in this direction, which is going to be right there. And we know it's 120 because this will match up to 120 up here. Kind of the easier way to plot negative numbers is I'm going to find 120. I'm going to find 120 on my unit circle. I'm going to go to the origin. Now, rather than going up a positive 2.5, right, 2.5 would be a positive 2.5, I'm just going to go in the opposite direction. So I find this line, and I go in the negative direction 2.5, and I plot my point there. It's probably the easiest way to plot negatives. All right, otherwise you have to kind of invert this to figure out what I do. So I find 120, and I go in the negative 1, 2.5, and I put my point right there. So 120, 2.5 is about there. So just as a reminder, we find our 120, and we go in the negative direction. So 120, I go in the negative direction, 2.5. All right, I want you to find the rest of those points and go ahead and plot them. If you get done early, go to the next graph and plot those as well. Okay, we don't have a ton of time, so these are the points you should have gotten. These are the points you should have gotten. And let's just go over some of them. So like I said, if we did 150, you should come up with cosine of 150 is negative 0.87, which is negative 4.4, which means my length is negative 4.4, and we have 150. So we're negative 4.4, negative 1, 2, 3, 4.4, and we're going to go around this direction. All right, so when I follow this line, it should be at 150. It is. So I could have found 150, and rather than going in the positive direction towards the number, I would go away from it 4.4. So that would give me that point. And these are all the points. And we should have noticed that, hey, this looks like a circle. And in fact, it is a circle, and we'll graph it in a little bit to see that it actually is, in fact, a circle, and our calculator can actually graph this circle. If you were struggling with plotting these points, you need to practice these. These were part of the homework. You need to practice them. I think the hard part is the negatives. But you have to look at your notes that when it's negative, you go around that way. So if you struggle with the negatives, make sure you look over your notes again. Okay, so we just come up with a circle. And if we notice the diameter of the circle is 1, 2, 3, 4, 5. Do you think it's a coincidence that this is 5 cosine theta? And it's got, yeah. No, it's not a coincidence. So if this was 10 cosine theta, it would have a diameter of 10. If it was 20 cosine theta, it would have a diameter of 20 and a radius of 10. So this number tells me the diameter of my circle. We're going to go ahead and plot these points. I just want to point out, like I said, this was an old edition. This should say sine, because it wouldn't make sense to find cosine, multiply it by 4, and all of a sudden suddenly it's sine. That wouldn't make any sense. So this is supposed to say sine theta. These are all sine theta. I didn't feel like wasting time because we had short class periods to find all those. And in fact, we did less points. So I'm going to plot that first point, which is 0 degrees, which is just the pole or origin. My next one is 2.8, 45 degrees. So at 45 degrees, I go 1 to 2.8. So that guy's right there. And we'll note that that's at 45 degrees. And it's positive, so I'd go in that direction. If it happened to be negative 2.8, I would still be on the 45 degree line. I would just go negative 2.8 instead. But this one's positive. Then we have 4 at 90 degrees. So that's going to be straight up and down. 1, 2, 3, 4. Oop, wrong color. So you should have a point here. And then we're going to have a point 2.8 at 135. So I'm going to locate 135. I'll follow that thing. It's positive. So we're going to go up 2.8. 1, 2.8. And it's a lot less points. But it is in fact going to also be a circle. And it has a circle of of diameter 4. It's just if it's sine, it's going to be up here. If it's cosine, it's going to be off to the side. Okay, if it was negative cosine, it would be on the other side. Just like if it was negative sine, it would be down here. Okay, let's prove to ourselves that this is true. We could have made mistakes. We're humans. Our calculator doesn't make so many mistakes, though, so we're going to let our calculator tell us whether we did this correct. So the notes are up there, but I'm going to actually walk you through how to do it. All right, let's go ahead and get my calculator out. Let's pretend like I'm not there. So the first thing you're going to do is you're going to hit your mode button. You're going to hit your mode button, which is right here. And then you're going to scroll down. And you're going to notice it says function, pair, that stands for parametric, pole stands for polar, and this is a sequential graph. So you're just going to scroll down, and yours should probably have function highlighted, and you're going to move over 3, you'll have polar flashing, you're going to hit enter. The second thing you're going to do is make sure you're in radians. Alright, degrees will work, but degrees sometimes messes stuff up. Radians, your calculator does a much better job doing radians because polar equations can get very complicated graphs really quick. So we're making sure we're in polar and we're in radian. Alright, as soon as we're in those two modes, go ahead and hit y equals. And you'll notice it doesn't say y equals anymore. It says r equals. And what I want you to do is go ahead and hit your x button. Pretend like you're doing y equals x. You no longer have an x. You now have a theta. All right, tells you're in polar equation. So what we're going to do in, what equation did I graph first? So we're going to go ahead and graph just that 5 times cosine of theta. So we're going to type in 5 cosine of theta. We're going to hit enter and we're going to hit graph. If yours doesn't graph or something weird happens, go to your zoom button and go down to standard, which is 6. So you can either scroll down or hit 6. And now all of our graphs should look the exact same. If you hit zoom 6, your graph should look exactly like mine. Tell me if yours does not.
What does it say?
They're better ones. They're much better ones. Sophia, is yours not working?
No, it's fine. She just says the window.
Oh, okay. Just hit zoom standard. Zoom 6. I think it's 6. I don't know what calculator I have. Yeah, Mike.
No. I'm just like looking for a high.
Oh, okay. Did that fix it, Sophia?
Yeah.
Okay. All right. So all our graphs should look like that. Does that look like what we put on our sheet? Yeah, we have a diameter of 1, 2, 3, 4, 5. Our circle is going to look a lot like that. Okay, let's graph a little more complicated problem. All right, we're going to do that example that's on the back side, or on page 343. Yours is probably already flipped. What was that? That's what we're doing. We're plugging in our calculator.
That's it?
Yeah. So we're going to type in 3 Sine of 2 theta. And then we're going to hit graph. So we have a 4-leaf clover. All right, there's ones that are actually called 4-leaf clover. So as you do your homework, I actually named a bunch of them and what their names are. So we have a nifty little 4-leaf clover that just keeps going around and around and around forever and ever. Now, how I want you to plot this, I'm not looking for perfection. All I'm asking you to do is count, well, this is 1, 2, well, it's hard to kind of see where it ends. So what I'm going to hit zoom, and I'm going to scroll all the way down, and I'm going to go to zoom fit. Yeah, mine has a huge delay on it. Zoom fit on mine is 0. It might be on yours, but zoom fit is 0 on mine. And we'll see it zooms in a little bit. Okay, so what I'm going to notice and how I'm going to graph this is I'm not looking for specific points. I'm kind of looking for this point up here that forms this clove. Well, it's a little past 2 on our y-axis here. And it's a little past 2, 1, 2 on this axis too. So all we're going to do is we're going to go to our homework, or our notes, and we're going to look at our graph, and we're going to say, well, I said on our vertical axis it was a little past 2. So I'm going to make a little tick mark past 2. And then I said on my horizontal axis is a little past 2, 1, 2, so I'll make a little tick mark there. And so where those two lines would meet up, that's going to be the tip of that clove. So then I'm just going to draw that part of the clover. And everything else is going to repeat, so down below it's going to be a little past 2, so I'm going to make that mark here. That will be my lower one. Let's go in the negative direction a little past, so I can kind of see where I'm making my mark. My other clove is here. And my final one is going to be out here. So I'm not looking for perfection. Good thing you guys are taking notes on what I'm looking for. So that's exactly what I'm looking for on the test. If I put this on a test, that is the exact process I'm asking you to do. Not perfection, but I'm looking for at least like those tips of those cloves being where I put them. Is yours not showing up?
No, it is. I got it.
Oh, okay.
I just plugged in the wrong thing.
Oh, okay.
It's still the clover, but it looked.
Okay. Gotcha. So that's what I'm looking. I'm just looking for those key points. Okay, let's go ahead and graph the next one. So we're going to graph r equals theta. So I'm going to go y equals. I'm going to put theta in. I'm going to hit graph. And we're going to notice I can't even see the whole thing. That's because we're still zoomed in from the last time. So every time you get to one of these, either do zoom standard or do zoom fit. Zoom fit usually does a pretty good job of it. All right, so this forms a spiral. This forms a spiral that has lots of key points that we can do correctly. So if we look here, we started at about 0, 0. So we should have a point starting at 0, 0. Then I'm going to look at my vertical axis. It crosses at about halfway up here. So it's 1 and then a little bit more. So I'm going to make those 2 points. Let's just stop there. So we start at 0, 0. And then we go up to a little past 1. So that's my first curve. That's the start of it. All right, then we look at our horizontal. Well, it goes at 1, 2, 3, a little past 3. So I'd make a mark there. So 1, 2, 3, a little past it, make my mark. So that continues there. Then I'm going to notice here it goes 1, 2, 3, 4, a little past 4. actually a little more past. And then this one is 1, 2, 3, 4, 5, 6, a little past our 6 tick mark. So I go 1, 2, 3, 4, it's about halfway past 4. And then 6, it was just barely past 6. So 1, 2, 3, 4, 5, 6, it was just barely past it. This is all my calculator can graph. But in truth, this spiral actually continues. Alright, it continues forever. It gets bigger and bigger and bigger and bigger. It's just our calculator just stops on that one revolution. Our calculator just does one revolution of polar, and then it stops most of the time because it thinks it's just going to continue. So you have to be smart enough to realize your calculator stops here, but it would actually continue spiraling out and out and out. And this shape is a form of what's called the golden ratio. If you're an art person, you should have heard the term golden ratio before, no? But it's very big in art, it's very big in nature. Let me just show you a couple pictures that work with the golden ratio. So if you're an art person, very famous paintings like the Mona Lisa, I think we've heard of that, follow the golden ratio. Alright, it's been discovered that art, before we actually knew about this golden ratio, followed this because this ratio is very appeasing to our eyes. It's also big in architecture. One example of the architecture, maybe you've seen this building before. Pretty sure it's in New York somewhere. But that follows the golden ratio, and a lot of architecture follows the golden ratio. On top of architecture and man-made things, a lot of items in nature, and these are just quick examples because we don't have a ton of time, follow the golden ratio. In fact, the dispersion of seeds within flowers follows the golden ratio. So we can draw this arc and we can predict the different petals. Obviously in nature everything isn't perfect, it just gets close to it, but it is scarily close. If you think of like a snail shell, that follows the golden ratio. You can picture that spiral. That spirals out. That follows the golden ratio as well. What time are we done?